This is going to be the last regular lecture before our final exam. If you have any questions over anything we've covered this semester, I will end up putting a discussion section down there, and please bring up anything you'd like me to end up giving to you for next Tuesday morning. Otherwise, our final exam, the way I'll do it, it will be on Georgia View. It will be under quizzes. It'll be called exam. It'll call the final exam. Just like now, your exam 3, if you haven't done it already, exam 3 is also in Georgia View. You'll have also a 2-hour limit to work on that. There's a 2-hour limit for your final exam, but you will have 24 hours from 10 a.m. on Wednesday until 10 a.m. on Thursday, which is whenever everything has to be in. If you have an issue where you can't do it at any point during that 24-hour period, let me know, and I may be able to push the time backwards a little bit. The forward time, we've been told we cannot move it forward, so it must go backwards in time from before Wednesday instead of after Thursday at 10 o'clock. All right, so now our last topic, we're going to end up starting to look at nuclear decay kinetics. And except for electron capture, everything involving nuclear decay involves just one object, that nucleus that ends up undergoing decay. And so because of that, the rate of the reaction is determined by how much stuff you've got. So if you have twice as much material, that you'll get twice as many decays. And half as much material, you get half as many decays. And so that may sound kind of, well, okay, that sounds kind of obvious. It turns out that that's one particular kind of a reaction called first order. And first order means the derivative of how much you got, the rate, how much it changes, of course, will be going down because it's decaying. So the first derivative of the amount you've got will be proportional to the amount you have. And when you take the integral of that, you end up finding that the amount that you have left over, which in the symbol I gave you was A, will equal the amount you began with, which was A subscript 0, times natural exponential of minus a constant times t. And where that t is whenever you're measuring it, measuring the value of just A without the subscript 0. So what will A be? So A could be in grams or whatever unit like that. It could end up being counting objects, so it could be in moles. But another thing that's sometimes easier to measure and is often also more practically important is what would be called the activity of it. Activity is the rate at which, in bulk, you're seeing decays happen. And the SI unit for that is 1 decay per second, and that's called becquerel, BQ. There is an old unit that's called a curie, which is a big unit. It's 37 billion becquerel is 1 curie. Becquerel is kind of a small unit, so you end up seeing kilobecquerel and megabecquerel frequently. Curie is a colossal unit. If you are exposed to a curie of stuff, you're probably not going to make it for very long. So you see microcuries and nanocuries and picocuries and stuff. If you saw anything with this on the exam, we always do things in SI or modified SI, so it would be in becquerels. If it was anything like that, you're not going to see curies, so don't worry about that unit. What a curie is the activity of 1 gram of pure radium-226. That half-life is something that you would have heard of. We've mentioned before, and I didn't end up defining it before because you'd already heard of it almost all used from chemistry beforehand, but explicitly half-life is the amount of time it takes for the quantity of a material to be cut in half. And so the relationship between that and the K in that formula is that your half-life is natural log of 2 divided by the K in that formula, and it's easy to do the math to be able to show where that comes from. The only thing that does not strictly undergo decay by first order, in fact, even things that are electron capture, almost all of them still are pure first order. The weird oddball exception is beryllium-7. Beryllium-7 does undergo electron capture to become lithium-7. And beryllium is atomic number 4, so it also is an alkaline earth. So in chemical bonding, it has a tendency to lose those 2 electrons. So what's left in the core is going to be just the 2 electrons in 1s. So what happens then whenever you end up having crystal of either metallic beryllium or of certain types of beryllium compounds, if you end up squeezing a crystal a lot by increasing pressure, what can happen is it can squeeze in that outer orbital, because that's the only one that will happen. But in this case, the outer orbital is 1s. So it can squeeze the 1s electrons, and because that happens, more of them get packed in toward the nucleus. And for that reason, beryllium-7, it's possible to end up increasing it by putting on as much pressure as we can end up reasonably making in a lab. By increasing the pressure, it can go up by about 10%. So, but everything else, you could put electric fields around it, magnetic fields. As long as you don't have something that actually can blow the nucleus apart, as long as you don't shoot particles at it that can hit the nucleus, that's the rate. I mean, it doesn't do anything. It's always going to be that rate. And there's nothing that we've ever been able to find to end up changing that. Okay, the next thing we'll talk about is dosimetry. So radiological damage to things, the way that you end up measuring it, it turns out that for the same kind of radiation, that the degree of damage you get is based on the amount of energy lost by the ionizing radiation. So sometimes ionizing radiation will come in and go out the other side. So it's how much is deposited, how much is lost in the way before it would go through. But it's how much is lost per unit volume. So, and energy is joules, so 1 joule per cubic meter is called a gray. And so that would be the, and that one is in some ways the hard SI unit, but the hard SI unit in that case is not quite as useful because different types of ionizing radiation, so neutrons versus electrons versus alpha particles, will end up causing different degrees of damage even with the same amount of energy. So in order to be able to describe how much practical damage is done, you end up multiplying basically the number of grays by a constant based on which type of ionizing radiation it is. And that product is called a sievert. So if you're talking about trying to give quantitative descriptions of how much damage happens to a person due to radiometric damage, it would be in sieverts. So typical numbers that you see would be microsieverts, nanosieverts, millisieverts is starting to get significant. It's not at the point where it's going to kill you. Sieverts, on the other hand, more than a sievert or so is very, very bad. A sievert will give you radiation poisoning, and if you have 4.5, you're going to either die of cancer or you're going to die faster than that. So if you get more than about 8 or 10, you're not going to live very long at all. All right, then we will break here.